Infrastructure deployment is moving away from software-based provisioning. The new standard relies on strict, hardware-level micro-firmware verification. Across enterprise engineering teams, the conversation has moved past software backends to the specific security requirements of the firmware layer. NVIDIA is driving this transition by standardizing confidential computing across its entire hardware ecosystem. The physical complexity of the NVIDIA GB300 NVL72 rack shown here necessitates this level of control. Such hardware density requires security independent of software. These systems utilize cryptographically sealed vBIOS and GSP firmware to ensure that only verified code can execute on the GPU. If the local firmware identifies unauthorized network routing, it is programmed to shut down the entire GPU cluster immediately. A shutdown is also triggered if the system detects any attempt to alter the host execution path. These restrictions make it impossible to deploy unregulated custom cloud stacks that bypass enterprise security protocols. Understanding this environment requires a deep dive into isolated execution zones and the mathematical verification of device attestation. Because hardware now dictates the boundaries of software behavior, the roles of software engineer and system security architect are effectively merging. To understand the need for these hardware locks, we have to look at the structural flaws in legacy cloud security. For years, cloud isolation was the responsibility of the hypervisor, a software manager for virtual machines. The industry operated on a simple premise: if the host operating system was secure, the applications running on top of it were safe. Massive AI infrastructure, which often involves multiple tenants sharing physical resources, has proven this premise to be insufficient. In modern AI deployments, the application can no longer treat the host server as a trusted environment. This diagram illustrates the shift. On the left, the traditional model assumes a secure host. On the right, the modern threat model treats a compromised host as a baseline reality. Attackers can use PCIe base address registers to move data around the OS layer entirely. This allows them to spy on raw GPU memory without the host operating system ever detecting the breach. They can even modify instruction sets before those instructions reach the processing cores. Software patches are ineffective against these hardware-level vulnerabilities. Isolation must be enforced by physical components that the host OS cannot touch. NVIDIA's solution is to create a physical perimeter on the chip itself, the Compute Protected Region, or CPR. This architecture separates the untrusted physical host at the bottom from the secure GPU at the top. Between them sits the staging buffer, the only authorized path for data. This lockdown is comprehensive, isolating up to 90% of the ultra-fast HBM3E onboard memory. The host OS has no ability to read data within this zone. It is physically blocked from writing to it, and it cannot inject code into the region under any circumstances. Any data moving between the host and the GPU must pass through an encrypted staging buffer, which acts as a mandatory transit bottleneck. The local micro-firmware continuously monitors this buffer for any signs of manipulation. If the firmware detects a mismatched encryption key, it halts execution instantly, protecting the data in the CPR. This security is not based on a software configuration, but on the immutable physics and cryptographic protocols of the hardware. If we cannot trust the central OS, how do the individual hardware components know they are talking to a secure partner? They verify each other using a framework called the Security Protocol and Data Model, or SPDM. Before any code runs, the micro-firmware generates a signed attestation report. This report contains a cryptographic measurement of the hardware state, the vBIOS, and the driver environment. If those measurements differ by even a single bit, the validation fails. Without a perfect match, the system refuses to negotiate the symmetric encryption keys required to move data. This image highlights why this matters for the Blackwell platform. Features like full performance encryption and trusted execution environments, or TEE, ensure that data remains secure even as it scales across 5th-generation NVLink topologies. This level of security is a requirement because deep learning architectures are significantly more complex than basic neural networks. A local classifier might handle small data sets with low risk, but a massive deep learning pipeline involved hundreds of gigabytes of distributed context that must be protected. Without understanding these hardware-level cryptographic limits, developers risk building leaky applications that are unsuitable for enterprise deployment. For those preparing for the 2026 job market, these technical changes dictate a new professional strategy. First, you must stop designing pipelines that assume the underlying environment is secure. Second, you must learn to build software that interfaces natively with confidential virtual machines. This means structuring code to run specifically within encrypted memory spaces. The industry is moving towards zero-trust architectures, where security is verified at every hardware node. Mastering hardware root-of-trust frameworks is becoming the baseline for infrastructure engineering. The highest-paid engineers are infrastructure architects who understand how code behaves when compiled onto hardened, regulatory-compliant enterprise hardware platforms. NVIDIA's firmware enforcement demonstrates that unregulated off-grid development stacks are no longer viable for enterprise AI. Let me know in the comments if you want a technical breakdown on configuring secure containers within hardware-attested environments. Success in this field now requires a dual mastery of high-level software abstraction and the physical, immutable constraints of the hardware security layer.